All right, so for part 3 of this video series, we're going to look at how we can regulate the glomerular filtration rate, or GFR. Okay, we've talked about all these other various components, but now how do we regulate it? That's going to be the key issue. So let's look at a couple things. So how to regulate glomerular filtration rate. And that's what we're going to be looking at on this one. Okay, so there's going to be 2 ways we're going to be dealing with this. Okay, your first way, and I'll probably do this on 2 different videos so the videos aren't too long. So the first one's going to be by intrinsic mechanisms. And what I mean by intrinsic mechanisms, those are those mechanisms that's controlled within the kidney itself. Okay, and we'll go into more detail in this video. The second way that we're looking at on this one is going to be extrinsic. Let me add to the intrinsic: controlled within the kidney. Okay. Extrinsic are those factors outside of the kidneys controlling the kidney. So this is going to be your nervous system, and your endocrine system, and that's going to be hormones. Okay, so those are your two different factors that we're going to consider. So what I want to do now is to look more specifically at the intrinsic mechanisms. Okay, so let me go here and let's look at the intrinsic. Oops, let me do this. Intrinsic mechanisms. Okay, intrinsic mechanisms essentially respond to stretching of the afferent arterial. So this is responds stretch or lack of stretching. Okay, so this is going to be responding, and there's going to be the 2 mechanisms associated with this one. Okay, so your 2 mechanisms is going to be myogenic response. Myogenic, that word myo should automatically get your mind thinking muscle. Okay, so this is going to be kind of a muscle response to this. The other one is going to be tubulo-glomerular feedback. So glomerular feedback mechanisms. Okay, and this one is going to be dealing with the juxtaglomerular apparatus on that. So first, let's look at the myogenic response, see what happens on this one more specifically. So let's bring this one up. Let me close this out, do a new layer here. Okay, so here is your basic renal corpuscle. This is the overview of the glomerular capillaries in the center. Here we have the afferent arteriole. Okay, this is the area that we're looking at. Okay. Just as a point, this is the efferent arteriole. You can see the differences in size between the afferent and efferent arteriole. Okay, afferent is going to be under much more control. On how we can control this with blood pressure. Okay, now blood pressure is going to be different than glomerular pressure. Okay, because we want to maintain consistency of glomerular pressure, which is going to give you more consistency with your GFR, glomerular filtration rate, okay? So if your blood pressure rises, okay, so incoming blood pressure, okay, we've got incoming blood in this area. Can you see if you have an increase in blood pressure that would stretch the afferent arteriole? So if you have more pressure in here, it would stretch it, okay? So what's happening are, let me put these in green so you can see them. Those cells in this area, okay, those are modified. These are going to be the cells that deal with vasoconstriction and vasodilation, okay? If you stretch those muscles, okay, for the blood vessel, the body's response is to, well, one, it wants to maintain consistency within the glomerular pressure, okay, within a region. So when they stretch, your body's response is to constrict them. So if they stretch, they're going to be constricted. They're going in. The next thing, that's going to decrease the blood flow going into the glomerular capillaries. If you decrease the blood flow going into the glomerular capillaries, you're decreasing the pressure within the glomerular capillaries, which decreases the hydrostatic pressure of the glomerulus, which then decreases GFR. Okay? Try to follow along. Once we get through a couple of these, we're going to go through a table and I'll spell it out. Okay? So what I want you to do is just kind of listen right now. Don't worry about writing notes. Okay? Here in a few minutes, we'll get to the writing of the notes. If you have a decrease in systemic blood pressure, okay? So we have a decrease in blood coming in, or blood pressure coming in. You should be able to now know that you have less stretch of the afferent arteriole. So if you have an increase in blood pressure, they stretch, and your body's response is to then constrict the afferent arteriole. If you have decreased systemic blood pressure, you have less stretch on the afferent arteriole, and your body's response is to then dilate that afferent arteriole. If you dilate the afferent arteriole, that sends more blood into the glomerular capillaries, which increases the hydrostatic pressure of the capillaries, which then increases glomerular filtration rate. All right, just kind of think about that for a second. Now get ready to take the notes. So let's look at this little fancy table, okay? So again, this is going to be associated with a myogenic response. So if we have let's see, what do we want to do with this one? If we have where's this? I'm on two different pages here. I'm sorry about that. If we have a decrease in systemic blood pressure, okay, what is that going to do to the stretch of the afferent arteriole? If we have a decrease in blood pressure, that decreases the stretch. ETCH. That's stretch, believe it or not. Okay, so that decreases the stretch of the arteriole. So what's that do to the glomerular blood flow? Okay, if you have a decrease, well, let's look at first. What's it going to do to the afferent arteriole? That is going to vasodilate the afferent arteriole, which is going to increase the blood flow. And if you increase the blood flow, what's that doing to the hydrostatic pressure of the glomerulus? Okay, so let me kind of do this also. Hydrostatic pressure of your glomerulus will increase. And when you increase the hydrostatic pressure of the glomerulus, that's going to increase your glomerular filtration rate, which then increases the filtrate, and then urine, okay? Now, if we have an increase in systemic blood pressure, what's that doing to the afferent arterial? It's causing an increased stretch. That one's spelt a little bit better, isn't it? You have an increase in stretch of the afferent arterial, which causes vasoconstriction of the afferent arterial. If you have vasoconstriction, what's that going to do to the blood flow within the glomerular capillaries? That's going to decrease the blood flow. And what's that going to do with your hydrostatic pressure of your glomerulus? That's going to decrease it. You decrease the hydrostatic pressure of the glomerulus. What's that do to your GFR rate? That's going to decrease your GFR. Okay? Rewrite this table and kind of spell that stretch out a little bit better. That kind of is bad. All right? So that's what we're looking at on the myogenic response. Okay? So decrease in blood pressure, decrease in stretch. That causes dilation of the afferent arterial, which increases the blood flow, which increases the hydrostatic pressure, which increases GFR. If you have an increase in systemic blood pressure, you have an increase in stretch, vasoconstriction, which decreases the blood flow, decreases hydrostatic pressure, decreases the GFR. All right? So now we have that one. So let's look at another thing here. Not the best picture, but it'll work. Okay, so let me go back with the black here. All right. A couple things that I wanted to point out on here. So we have our afferent arterial coming in, efferent arterial. So afferent going in, efferent coming out. Okay. So now let's look at the tubuloglomerular feedback mechanism and what this is dealing with. This is focusing in on the juxtaglomerular apparatus. And the one thing I don't like about this picture, it's really not aligned up great. But the juxtaglomerular apparatus, I'm trying to come up with a color that's a little different from all this. Juxtaglomerular apparatus is going to be in this region, okay? And that juxtaglomerular apparatus is made up of, let me do it this way. So the juxtaglomerular apparatus is made up of macula densa, and granular cells, okay? Macula densa cells are going to be part of the distal convoluted tubule and the distal end of the ascending limb of the loop. Okay, so if you have the loop of Henle and you have a descending limb, turns around, then you have an ascending limb. And that ascending limb then goes into your distal convoluted tubule. Roughly at the area for the distal convoluted tubule, it's in between the afferent and efferent arterioles. And where the tubule comes into contact with the afferent arteriole, you have specialized cells there that make up the juxtaglomerular apparatus. Now on the tubular side, you have cells that are called macula densa cells. On the afferent arterial side, you have specialized cells called granular cells. Okay? Now the macula densa cells, now we're on the tubular side. The macula densa cells on here, they are sensitive to and will respond to sodium chloride levels. So let's go down here. So let me keep the picture in frame. So macula densa they respond to sodium chloride levels. Okay? Now, if you have high levels of sodium chloride in your tubular fluid, okay, so that's what we're looking at. So if you have high levels of sodium chloride within the tubular fluid, what that's causing is that's going to cause vasoconstriction of the afferent arteriole. Okay? Another thing that it does is it causes constriction of mesangial cells. Now, I haven't talked about what the mesangial cells are. It does a number of different things. In this picture, this is the green stuff, okay? That's extraglomerular mesangial cells, okay? You also have, let me put green in here. So we're going to have mesangial cells in here. So these are in between the capillary loops, okay? Those are also going to be mesangial cells. And one of their functions is the ability to constrict. And when those constrict, it actually will decrease the surface area of the glomerular capillaries. So if you decrease the surface area, you are going to have less fluid coming out. So if we have increased surface area when we breathe in our lungs, it allows more gas transport. If we have increased surface area in the small intestine, we can absorb more nutrients. Okay? If we have decreased surface area in your small intestine, that's why we have these microvilli and all that. If we decrease the surface area, you have less absorption. Here's the same thing. If we decrease the surface area of the glomerular capillaries, we're going to decrease the amount of fluid that can come across. Now, this is a secondary thing. I didn't really spend a lot of time at all on talking about mesangial cells. That's not my primary concern. The other ones are a much more relevant component. Okay? So the last thing I want to talk about, let's see, do I have room? Last thing is, what do I mean by systemic blood pressure? Now, in the terms of the cardiovascular system, blood pressure, standard blood pressure, 120/80, that kind of stuff, that's not exactly what I'm referring to in this case. In this case, I'm referring to the mean arterial pressure. So we're looking at MAP, or mean arterial pressure. Okay. I wonder how you figure that one out. So we're looking at the mean arterial pressure. Now, your afferent arteriole responds to MAP, mean arterial pressure. And it responds to a range of the pressure. The range goes from a low of 80 millimeters of mercury to 180 millimeters of mercury. That's what it responds to. Okay. Now, 80 is going to be associated with a low blood pressure. 180 is going to be associated with a high blood pressure. At 80 is your minimum amount of pressure in the afferent arteriole that will cause it to respond. So this causes a maximum dilation, or let me do vasodilation, of afferent arteriole. Okay? 180 causes causes the maximum constriction of afferent arteriole. Now, if it's lower than 80, so let's say you're bleeding out, okay? You cut an artery and you're bleeding, so your pressure really drops. The glomerulus or the afferent arterial can't respond any more than it can at 80 millimeters of mercury or 180 millimeters of mercury. At that point, we have other issues to worry about. So these are the intrinsic factors that I want you to know. Next video, we're going to look at the extrinsic factors.